Today I'll be explaining the basic concepts behind artificial neural networks and the maths that underpins them. I'm assuming that you have a good grasp of linear algebra, but have done little or no programming. Machine learning is the study of computer algorithms that improve automatically through experience. It is seen as a subset of artificial intelligence. Traditionally, software engineering combined human-created rules with data to create answers to a problem. Instead, machine learning uses data and answers to discover the rules behind the problem. An artificial neural network is simply a computational analog for the real neural network that is the human brain. A neural network can perform regression, working out pattern data and predicting outputs using input values that haven't been seen before, and also categorization, which is the process of categorizing an item into a discrete group based on certain variables. The simplest neural network configuration consists of a series of neurons arranged in 3 layers. Each neuron is simply a value between 0 and 1, constrained by an activation function, that is the sum of the weighted neurons that connect into it. These layers are known as the input, the values given to the neural network, the hidden layer, the values calculated by the network, and the output. These neurons are connected by weighted edges called synapses. At the top of the diagram on the right, you'll see the bias. This is a small value that is added to the sum. I'll discuss its purpose later in the presentation. So as you can see here, the value of a neuron is the sum of the products of each connected neuron multiplied by the weights of the respective neurons, with the bias added at the end. This value is then passed through the activation function. The purpose of activation functions is to force a disruption of linear behavior in a neural network. This gives the network the ability to form regions that are far more complex as its output sets. If the activation function was linear, it would be impossible to use gradient descent to train the model, since the derivative of a linear function is constant, and thus the network would be unable to learn. A neural network with a linear activation function is simply a linear regression model. It has limited power and ability to handle complexity. The range of the activation function is usually restricted between -1 and 1. Without the range restriction, there would be situations when it would be optimal for the neural network to create an asymptotically large weight. If this occurs, the network will behave linearly, defeating its purpose. The most common activation function is the sigmoid, but there are also alternatives which provide the network with different properties. For example, linear truncated functions such as ReLU are sometimes used. By using different activation functions, the shape of the lines that bound their categorization feature can be altered. In general, only nonlinear activation functions are used for complex networks. Forward propagation is the process through which the input values are manipulated within the network in order to produce an output. Forward propagation is the process through which the input values are manipulated within the network in order to produce an output. Since a neuron's value is defined as the sum of its weighted inputs passed through an activation function, the neurons of the simple neural network on the left can be expressed as this. In a larger network, this would be a very time-consuming set of calculations. To remedy this, the set of pairs of input values can be expressed as a matrix, where S is the number of input pairs used. The first set of weights can be expressed as this. The default value for the weights is set to approximately 0.5, with a small degree of random variation. The matrix Wn is defined as the matrix of weights for the synapses connecting the nth and n+1 layers. Multiplying these with only one pair of inputs gives this. By adding more input pairs in the rows of the input matrix, it is possible to output values for the hidden neurons for more than one pair of inputs at a time, significantly increasing the speed of the computation and the training process. The inequality at the top of the page can also be represented as this, where W1 is the matrix that waits for the first layer of multiplication, Z2 is the matrix of values for the column on the visual diagram of hidden neurons, and W is the matrix of input values. After the activation function is applied, the inequality can also be represented as this, where A2 is the matrix of activated values for the hidden neurons in the second layer. The same method can then be used to propagate the values from the second to the third output layer, where W2 is the matrix of weights for the second set of multiplication, and Z3 is the inactivated matrix of output values. These values are then activated to produce the processed output, Y. The mechanism through which real neurons transmit information can be modeled remarkably accurately using a neural network with artificial neurons. The connections of the biological neuron are modeled as weights. A positive weight reflects a positive connection, while negative weights reflects a negative connection. All inputs are modeled by weight and sound. The activity is referred to as linear combination. Finally, an activation function controls the amplitude of the output. For example, an acceptable range of output is usually between 0 and 1, or it could be -1 to 1. In order for a neural network to be useful, it must be able to learn and adjust its outputs based on previous input data. This is done through a technique called gradient descent. Training an artificial neural network is essentially the process of minimizing the value of a cost function. The cost is a function of the inputs and the synapse weights. Since the input values themselves cannot be manipulated, the cost can only be minimized by manipulating the weight values. It is clear that finding the minimum value for our cost function by a brute force method of trying every combination of weights is too computationally expensive, especially for larger networks with tens of thousands of neurons. You would have all seen analogs to the cost function in the most recent statistics prep, where a regression line is found by minimizing the sum of the squares of the residuals. A similar process occurs here. The value of the cost function needs to be minimized, and this is done through differentiation. In order for a neural network to be useful, it must be able to learn and adjust its outputs based on previous input data. This is done through a technique called gradient descent. Training an artificial neural network is essentially the process of minimizing the value of a cost function. The cost is a function of the inputs and the synapse weights. Since the input values themselves cannot be manipulated, the cost can only be minimized by manipulating the weight values. It is clear that finding the minimum value for our cost function by a brute force method of trying every combination of weights is too computationally expensive, especially for larger networks with tens of thousands of neurons. You would have all seen analogs to the cost function in the most recent statistics prep, where a regression line is found by minimizing the sum of the squares of the residuals. A similar process occurs here. The value of the cost function needs to be minimized, and this is done through differentiation. The cost function j is to be taken as this, where the processed output is y hat. The cost function represents the sum of the errors for each set of training inputs, since y is the correct value of the output and y hat is the output that the network produced. The fact that a coefficient of a half is used is arbitrary. However, using it will usually make algorithmic computation of the cost easier further down. When these previous equations are substituted into jx, the result is an overall equation for the cost of the training inputs. To perform gradient descent by the Newton-Raphson method on the cost function, it can be differentiated to calculate the partial derivative of jx with respect to w. From this, we can now simply subtract a scalar, the training rate, multiplied by the backpropagating error from the weights for each layer of synapses. This performs gradient descent along the cost function. When the neural network is successfully trained, the error for the output is sufficiently low. The gradient descent is stopped. So overall, on the left, the processed neuron outputs are substituted into the cost function, and the equation on the right differentiates the cost function. After the final result is obtained, the product of the training rate and the backpropagating error from the weights of each layer of synapses must be subtracted. The training rate must be chosen carefully because it can cause underfitting or overfitting. After the final result is obtained, the product of the training rate and the backpropagating error from the weights of each layer of synapses must be subtracted. The training rate must be chosen carefully because it can cause underfitting or overfitting. Algorithm selection of the neural network is a crucial step in forming an accurate prediction. Deploying an algorithm with a higher rate of accuracy can be a difficult balancing act. The fact that each algorithm can produce vastly different models based on the hyperparameters provided can lead to dramatically different results. The process of finding a minimum point of a function for a gradient descent is heavily dependent on the learning rate. If the learning rate is too large, divergent behaviors may occur and the minimum point will never be found. Conversely, if the learning rate is very low, like in 4BD4, the algorithm will take a very long time to find the minimum point. Another constant challenge in machine learning is navigating underfitting and overfitting, which describe how closely the model follows the actual patterns of the dataset. To understand underfitting and overfitting, we must first understand bias and variance. Bias refers to the gap between the predicted value and the actual value. In the case of high bias, the prediction is likely to be skewed in a certain direction away from the actual values. On the other hand, variance describes how scattered the predicted values are. And of course, in an ideal network, both the variance and bias would be zero. Mismanaging the variance and bias can lead to results such as the model becoming too simple and inflexible, underfitting, or the model becoming overly complex and flexible, overfitting. An overfitted model would yield accurate results for the training data, but would be useless in formulating predictions from test data. Finally, After the neural network has been trained and properly configured, it can be used to categorize data or make predictions. Finally, if you're interested in learning more about this topic, I would recommend these two books. I found them very useful in understanding the underlying principles of machine learning.